Professor, I think you're muted.
Thank you. Yeah, I lost internet again here. We are recording, and now you can hear me, right?
Yes.
Okay, thank you. Let's see here. It's the internet. It's not the electricity. Electricity is not going out here. Looks like it's my internet service that's not very good. Even though I have an internet service that uses optical fibers. Okay, so we can even come up with a table of the conservative forces and their respective potential energy. Okay. So let's take a look here. Insert. Let's see how we're going to do. Let's see. Gravitational force, elastic force, electric potential energy. Yeah, okay, let's use this one and let's see. One's going to be the force, the other is going to be the potential energy. Force, potential energy. The easiest one is gravitational force nearby Earth's surface is mg. Well, we got to put a negative sign there as well, right? Force, if I make it a vector, mg, like that. And don't forget, it's a hat, okay? And the potential energy is going to be mgy. It doesn't have a negative sign. This one doesn't have a negative sign. Go. Gravitational force nearby Earth's surface. Now, center. And then we gotta write that down here, conservative forces, right? Conservative forces. We also have the elastic force. Elastic force, we saw that in physics 6, is going to be minus kx with an x hat. And its potential energy is going to be given, remember that, half. We do not have a negative sign there either, because this negative sign cancels out with the negative sign of the definition, right? Here you go. And I'm going to even put the definition. Okay. Let me write down the definition here. It's very important. Because the genetic definition is potential energy is minus the work done by a conservative force. Conservative force. Okay. That's the very definition of potential energy. Elastic force, but gravitational force the other gravitational force, universal gravitational law. Let's put it like that. Universal gravitational law. Here you go. It's better if you write down like that. Not nearby, but universal gravitational law. Universal gravitational law, comma, the gravitational distance. Okay, universal gravitational law is going to be minus, we are doing, mass of the Earth, mass of the object divided by its distance square, and we gotta put an r hat there as well. And when we calculate the potential energy of this force that you see right in here, you get something like that. Okay? Note that we do not have a lower m here, right? Note that we do not have a lower m here, because why is that? We don't have the lower m here because the potential energy is due to this central mass, the mass of the Earth. Oh, wait a minute. No. Should be I am here. Sorry. And I gotta fix that too. Yeah. Potential energy we do have in this case. In this case, we do have the other mass, yes. We do not have the other mass in the other potential, not in the potential that we're going to define, okay? That I'm going to define. Here you go. Universal gravitational law, and now Coulomb's law. Coulomb's law. Coulomb's law is like that. Don't forget, Coulomb's law is that for a point charge. Point charge. Okay, and it's not going to be G, it's going to be a K. Ramon is going to be, put it big Q, small q, like that. Okay? Divide by r squared. Is that a negative? No, we do not have a negative. I'm going to emphasize that by writing the positive sign in there. And when we calculate the potential energy of those two charges, big Q and smaller q, we get something, K, big Q, small q. I'm not going to derive that because it's difficult to derive, okay? Just remember, just memorize that. Point charge. And then, we also have one more here that I didn't tell you. Recall that the electric force is a conservative force. What else can I tell you? Remember that. Whenever we have, what about uniform E field? Here you go. We also have another conservative force, that uniform electric field. Just recall that the electric force, any electric force, is a conservative force. Okay? And there is also a relationship between the electric field and the electric force that we saw before. Okay? Recall. And the relationship is given by the following. Here you go. F is going to be given uniform by the Q times the electric field. We saw that before when we defined the electric field. Remember that? Okay. But in this case, we're talking about the uniform electric field. Now, what you see right in here is very similar to what you see right in here. Okay, here we also have a uniform gravitational field that is represented by the G nearby the Earth. The G is uniform nearby the Earth. It's always pointing towards, in the vertical direction, towards the surface of the Earth. And it doesn't change its value nearby the Earth field. So there is an important parallel between this conservative force and this other conservative force. They are both uniform. They are both uniform. Because they are both uniform, it also means that the potential energy, its potential energy, is going to have a similar equation, a similar value. Okay? The only difference here is that instead of M, we are going to have Q. Instead of G, we are going to have E. And instead of Y, we are going to have the X distance. Okay? And there is one more difference. We have a negative sign right in here. Okay? And it's possible to derive that just by using the very definition that you have right in here, the definition of the work done by the conservative force. Okay, that can be applied to this one using regular algebra and this one. In order to find those other two, we need calculus. Okay, and in order to find this one here, in order to find the potential energy of this one here using this definition that you see right in here, we need to do that graphical technique that I showed to you in physics 6. Okay? So here you go. Let's do that together so you can understand better. So here you go. We have the work done by the potential energy is equal to minus the work done by the conservative energy, right? In this case, let's do that for the uniform electric field. Let's do that for the uniform electric field. The work done by this conservative energy is going to be equal to the electric force multiplied by the delta X. Okay? That's how work is defined, right? Force times the distance, the displacement. The displacement. Okay, but this force can also be rewritten as being the electric charge times the electric field. Do you see here this equation and this equation? They are almost the same. The only difference here is the delta X, right? So how do we get from here to here? That's simple, okay? This delta X is X minus X naught, okay? And we set our X naught as being 0. Setting X naught equal to 0, we reduce the above equation to the one in the table, right? To the one in the table. And I'm going to label this table right in here. Oh, what's going on here? What I want, here we go. Let's see. Potential energy for different conservative forces, right? Potential energy. We still didn't get to the point of the potential. There is potential energy and there is potential. Conservative force. Okay, so here we go. Potential energy for different conservative forces. Let me shrink this table a little bit. I'm gonna shrink this a little bit as well. I'm gonna shrink this other one here. And then I'm gonna apply another column right in here. And this column is not going to be the potential energy. This column is gonna be something else. This column we are going to call the potential. Okay? And how is the next question is how the potential is defined. And the potential is a very important concept as well. We didn't cover the potential, the concept of potential in physics 6, but this is rather straightforward. Okay. So recall the above equation which reduces to its respective one in the table. Okay. Now, lot of things, right? And that's why I'm going to just remind you what we did so far, right? So here you go. We start with electric charge. Okay. I then introduce you to the electric force. Okay. And then I introduce you to the electric field. But in addition to the electric field, we also have the electric potential energy. That is right in here in this column. And by the way, we have the same thing. I'm even going to make a table comparing the mechanics parameter to the electric parameter. Okay, so here you go. Mechanical parameters. Okay? Mass. It's the respect and electrical parameters. The mass equivalent in the electric field is going to be the charge, the electric charge. Okay? And then I introduce you to the, let's say, the gravitational force. Right? And its electric counterpart is the electrical force. Okay? Gravitational field. What is the gravitational field? The gravitational field is the acceleration of gravity, okay? I didn't mention that, but that's what it is. And recall that the acceleration of gravity, what's the acceleration of gravity? It's just the gravitational force divided by the mass. And here, the electrical field is going to be similar. E is the electric force divided by the source of the electric force. That's how you should interpret what goes downstairs, okay? Here's the source of the electric force. Here's the source of the gravitational field. In addition to the field, we also have the potential energy. I need to come up with another. Here you go. I'm going to come up with another. Let's see how I'm going to do that. Yeah, I need to come up with another column here, okay? So it looks better. Okay, good. And now I'm going to, no, it's not what I want. I want to copy, I'm going to paste. Okay, mechanical parameters. Yeah, mechanical parameters. And here we're going to have, let's see, source of force. Source. Okay. The mass is the source of the force. The mass is also the source of the field. Okay, field, let's put it this way. And here you go. I'm going to define the field as being the force divided by the source. Okay, divided by the source. Mass is the source of the gravitational force. The electric charge is the source of the electric force. So the field is defined as the force divided by the source. Okay. And now that I put that writing here, I don't need that anymore, just to reduce my space. And now we have the potential energy, right? We have the gravitational potential energy, and we have the electric potential. I'm going to put P. Potential energy, I abbreviate by P, just to save space. Gravitational potential energy, PE. Electric potential energy. Like that. And then we have one more here that we didn't define in the mechanics. Instead of potential energy, we have what we call the potential. Okay? The potential is going to be what? The potential energy divided by the source of the force. Okay? Very important parameter here to define. And we are going to need that to do the lab. Okay? For the case of the potential, right? Potential of would be what? The potential energy, right? Divided by the mass. If the potential energy is the potential energy of a mass nearby the surface of the Earth, then the potential of this mass is going to be mgy divided by m, or gy, right? See? Is that for a uniform field? If we are talking about a point mass, right? That uniform field, right? If you're talking about a point mass, the potential of a point mass is going to be the potential energy divided by the mass, which, by the way, is going to be, let's remember here, that's the potential energy. Potential, let's see here. Yeah, this one right here. Universal gravitational law minus big G, big M, small m, divided by R, right? Ends up being divided by M. This M here canceled out. So the potential, the gravitational potential, is going to be big G, big M divided by R. That's for a point mass. And we can do the same for the electric field. If the electric potential energy is QEY, the potential of a uniform electric field is going to be minus EY. Just like we had, okay, uniform E field. Uniform E field. Let's see if I can shrink it a little bit more. No. I'm going to skip this step here to gain some more space. Okay. It's not EY, by the way, it's EX, because it's along the X direction. Okay. Uniform field. And then we can do the same for a point charge. Point charge. What we end up getting here is big M, K, big Q divided by R. I'm going to, that's the potential of a point charge. There is no small q in there because it's being divided. And here's the very definition of the potential, whether it's the gravitational potential or the electric potential. Let me highlight that. This one as well. Let's see if I can. Like that. Okay, I'm just highlighting here. And what else can we do? Electric potential energy, here you go. Now, electric potential, right? Electric potential. What you see right in here is exactly what you have right in here. Okay? And now we can add. Yeah, we already did that. We already did that. Okay. Potential energy. Let's see here. No. Potential. And okay, we have to take this one out. Potential. Yeah, we have to take this one out as well. And we have to take this one out as well. This one, let's see. This one, I'm going to just put a question mark there. Okay. Just going to put a question mark there. And the potential for this one is going to be the mass. Because what would be the source of the elastic force? The source of the elastic force would be K, right? So it would be reasonable. And by the way, the potential we usually represent by the letter V. Okay, let's put V here. Let's put V here. And let's put V here. Those are the parallels that we get. This one here, I'm going to leave as a question mark, okay? Because it doesn't show up in electricity. So you don't need that. Okay, so two different tables and one paragraph here showing the progression of the ideas, of the concepts, the progression of the concepts. And so why did I do all of that? Why did I do all of that? Okay, there is a reason why I did like all of that. There's a reason why we define the electric potential. We define the electric potential for a very simple reason, for a very practical reason. Electric potential for a very practical reason. It is much easier to measure the electric potential than to measure either the electric potential energy or the electric field, okay? It's much easier. The potential is a scalar quantity. Unlike the E field, which is a vectorial quantity. And on the top of that, we have very inexpensive devices that are capable of measuring the electric potential of a system. Okay, and this device is called the voltmeter. So I defined the electric potential for you, including the electric potential energy, right? Let's talk about, let us now talk about the units of the electric potential. It's time for our break, right? 49, yeah, it looks like it's, yeah, let's take another break before we start talking about the electric potential. Break, 11:50 a.m. to 12:05 p.m. Let's do it this way. Okay. In this meantime, look at the very definition of electric potential and do a dimensional analysis to find out what would be its unit. That's what we are going to do next. But I want you to try on your own as well, okay? Try to do that during the break. And then when we come back from the break, I'll show you how to get the unit of the potential. Okay, so see you in 15 minutes. Okay. I am back here. So now do you see where this idea of electric potential comes from? Okay, it all depends on the electric force that you are using. So from the above, you can see that the electric potential, you can see that the electric field, the electric potential energy and the electric potential, depends on the type of conservative force. Each conservative force, right, has its own electric potential. And the definition is given just by what I showed to you, right? The electric field is the electric force divided by a test charge, right? The electric potential energy. Electric potential energy is given in terms of the work of a given conservative force, and the potential, the electric potential, and we abbreviate the electric potential with the letter E, right? The electric potential energy, I'm going to abbreviate with the P, and the electric potential is just the potential energy divided by the test charge, right? Where Q is the test charge. Here too, Q, where Q is the test charge. Okay? Both the electric field and the electric potential are described in terms of a main charge distribution, right? Main charge distribution. That's what they describe. They describe describe both electric field and electric potential. Describe their respective parameters. Describe their respective parameters of a main charge distribution. It's better this way, of a main charge distribution. Okay. And why did I do that again? I did do that because there are devices out there that measure the electric potential in a much easier way. It's much easier for you to measure the electric potential than to measure the electric field or the electric potential energy. I have a device right here. Okay, this is a multimeter. Any multimeter that you're going to see out there has the capability of measuring the electric potential, but not the electric potential energy. And in order for you to get a device like that that measure the electric field, you need to buy a very expensive device. Okay, this one here doesn't measure the electric field, but it measures the electric potential. One more thing. Not only it is easier to measure the electric potential, but there is also a very simple relationship between the electric potential and the electric field. Okay? If you know, in other words, if you know the electric potential distribution throughout a given space, you can determine the electric field. Okay? And let me show you what the relationship is, exactly what the relationship is. And this relationship is like the following. I'm not gonna prove that. Okay, the electric field, for instance, is given by minus the change in electric potential divided by the change in distance. That's the relationship between the electric. So if you know the electric potential distribution throughout a given region of the space, you can use this relationship to find the electric field, okay? And that's what we are going to do in the lab on Wednesday. In the first lab on Wednesday, we will map the electric potential around a charge distribution, and we will obtain the genetic direction and even the strength of the electric field of its respective electric field. Yeah, good. Okay. That's what we are going to do. Let's see, someone is asking a question here. Let's see, so you can find the electric field. So you can find the electric field. That's right. That's one way of finding the electric field. And there is this other way of finding the electric field too, right? That's the second way of finding the electric field. Let me see the second part. And then you use the value and input in PE over Q to find the electric potential. That's right. Okay, so yeah, you have a good point there, Jeremy. You know, recall that E is what? F divided by Q, but E is also equal, right? To minus delta V over delta R, right? Delta V over delta R. So two different ways of finding the electric field, either from the force or from the electric potential. Okay? The electric potential. Okay, so let's take a look right here. Yeah. And it's all, those parameters are all related to the potential energy. Now we can go back. Now we can go back to the electric field, right? But let's not forget that we cover some of the sections of chapter 19. Let's take a look at. Here you go. We did cover the idea of potential energy. Let me put here on the side. Okay, chapter 19. 19.1, potential energy. 19.2, the electric potential difference, yeah, which is the electric potential. Okay, we covered that as well. Yeah, now 19.3, the electric potential difference of point charges. We covered that as well, right? Let's just copy what we had written down here. Here we go. point charge. Yeah. Electric potential difference of point charges. Right. You know, what I call electric potential is the same as the electric potential difference, okay? Here you go, the electric potential difference of two charges, okay? What else? Equipotential surfaces. We didn't cover that yet. 19, but it's exactly what the name says, okay? Equipotential surfaces and their relation to the electric field. Okay, what is in boldface was something that we covered. Okay, we didn't cover that yet, but we are going to cover this one in the lab. Okay, 19.5 capacitors and the dielectric we didn't cover yet. 19.6. 19.6 biomedical applications of electric potential differences. Okay, this type of thing is used to measure, for instance, the electroencephalogram. Okay, electroencephalogram is just one application of electric potential difference. Okay, and the electrocardiogram too. That's why you have electro there in the name, right? Have you ever also heard about the electromyogram, right? There is electroencephalogram, right? There is electrocardiogram. They all use the electric potential encephalogram, right? Let's see. Oh, here you go. And then we also have the electromyogram. I did this exam some time ago. Electromyogram, like that. They all use this concept of electric potential. Again, why? Because it's much easier to measure the electric potential than the other parameters that we are talking about. You can buy a $15 voltmeter or even multimeter, right? And you will be able to measure the electric potential of a system. Okay, 19.7, the Millikan oil drop experiment is an important experiment, the historical one. But we are not going to cover those two, okay? But let's take a quick look here in 19.6, since it's related to what you folks are going to see here. I cannot get. Okay, yeah, okay, good. Conduction of electrical signals in neurons, okay? That's one of the biomedical applications of electric potential energy, of electric potential difference, and electric potential energy too, right? And here you go, here's an illustration of a cell membrane, okay? Across a cell membrane, you can have a difference in electric potential. And the cell uses this electric potential difference exactly to do some work. All that work that's done in the cell is due to this electrical potential difference. And this electrical potential energy, this electrical potential difference has some electrical potential energy. And the cell uses this electric potential energy to do all those neat things to keep us alive, okay? Here is a sodium channel, an illustration of a sodium channel. Medical diagnostics technique, right? Several important medical diagnostic techniques depend on the fact that the surface of human body is not an equipotential surface. Between various points on the body, there is small potential differences, okay? There is small potential differences between various points on the body, and those potential differences can be used to make some measurements, for instance, can be used in electrocardiography, or even in electroencephalography, just like I mentioned before. And there is another one here, electroretinography. Okay, electrocardiogram is EKG, right? Here you go. We have a strip chart here. We are measuring electric potential between points in the human body. The potential difference generated by the heart muscle activity provide the basis for electrocardiography. The normal and abnormal EKG patterns correspond to one heartbeat. Okay. And look at an abnormal one, right? That's the normal heartbeat. That's abnormal one. Just by making those measurements with an and an electrocardiogram is just like a device like this one, okay? Used in a different way. That's what an electrocardiogram is all about. It's a multimeter that measures electric potential, and then you have to interpret the signals that you receive. Electroencephalogram is the same thing. Okay? You measure electric potential between two different points. Here you go. One electrode is connected at this point here, another electrode is connected here. Okay, and the electrode that we are talking about is just those two probes that I have here. One is the positive, the other one is the negative. Okay, a multimeter, they do have a positive and negative sign. And here's the electroretinogram, right? Here you go, normal and abnormal. Look where the electrodes are connected. Connecting the electrodes would be just like putting one probe here and another probe, apparently it's in the eye, right? But I'm not gonna put my probe in the eye. And that's what this chapter is all about. I'm not gonna ask you, I'm going to skip this chapter, okay? But I want you to know that the measurement of electric potential can be used in several medical devices out there, including the defibrillator, okay? The electrical energy in the defibrillator can be used to revive a patient. Okay, so it's 12:26 right now. I want now to go back to the chapter on electricity. We are going to examine this section more carefully during our experiment. We're even going to plot equipotential surfaces, okay? Capacitors and dielectrics is going to be after the lab. And now, let me also copy and paste the sections of chapter 18. I want to keep them next to each other. So going back to the electric field. Going back to the electric field. You already know what is the electric field of a point charge, right? You already know that. Let's see, I'm gonna get this one here. I'm gonna copy and paste right in here. Electric field of a point charge. Let me put that in vectorial format. K. And then I'm going to say electric field. One, electric field of a point charge Q. Okay, now I can do that. KQ over R squared. We also have uniform electric field, right? Uniform electric field. And the uniform electric field can be written down as, let's say, a constant. You know, a constant C, I'm going to write down that's a constant C, but instead of in the radial direction, it's going to be in the x hat direction. Later on, we are going to derive what's the value of this constant. Uniform electric field, you know, two parallel plates. Okay? Two parallel plates. And then there are other charge configurations that we can determine the electric field. Let me get them. Annular charge distribution. Annular charge distribution, right? So here you go. And I have an illustration of the annular charge distribution, the ring. Here you go. That's the one. Okay. It's very easy to calculate the electric field of a uniform annular charge distribution along this axis here that passes through the center of the ring. It's very easy. Why is it very easy? Because the distance of this charge to this point is the same as the distance of this charge to this point. It's the same as the distance of this charge to this point, and so on. Okay? It's like a cone, right? It forms a cone here. The difficult part is to get the electric field at a different point, a different spot right in here. That would be difficult. Okay? Uniform annular, I'm going to put here, uniform annular charge distribution. E field of a uniform annular charge distribution. We can also calculate the E field of a uniform linear charge distribution. E field of a uniform circular charge distribution. And this one here, E field of a spherical charge distribution. Of a spherical shell. Let's put this spherical shell. Let's put here a spherical shell charge distribution. A spherical charge distribution is going to be a little bit more difficult. Okay, and a field of a cylindrical shell charge distribution, different geometries that we can calculate the electric field. And we can do that using Gauss's law. Let me show you how we do that, okay? But before we can calculate all those electric fields, we can calculate all these electric fields using Gauss's law. But before I introduce you to Gauss's law, I must first define the concept of electric flux. Electric flux, okay? Gauss's law uses this concept. Gauss's law uses this concept. I'm going to give you an example. And from this example, I'm going to start defining what the electric flux is all about. Okay, so here you go. Oh, first, let me give you the definition, right? Let me give you the definition first. The electric flux is the electric flux is a scalar quantity. We represent it by this big phi equation. Okay. And this electric flux is defined in terms of the electric field, in terms of a imaginary surface area, and is the cosine of the angle between the electric field and the area vector of the surface. That's how we define, okay, for a uniform electric field, okay, the electric flux is given by the following equation. So let me illustrate that for you. I don't have it here. I gotta look at the other one. Illustrations. Gauss's law, right in here. Gauss's law, okay? So the best way of understanding the electric flux is by applying it to the case of a uniform electric field. Let's say we have a uniform electric field in space. We generated it, right? Right from this distribution, I can say that the positive charges associated with this electric field is to the right of this field, and the negative charges are to the left, right? The fields converge. The field not converge, but the fields point towards the negative charge distribution. If I come to you and say, look, I want to find out what is the electric flux of this electric field with respect to a given surface, okay? And then we are going to start with this simple surface here, planar surface. that's oriented at an angle of 90 degrees, okay, with respect to the field. Can you picture that? So try to visualize an electric field going from my right hand to my left hand, okay? The electric flux is defined with respect to an imaginary surface within this region, within this volume where we have an electric field. So if you have a uniform electric field from my right hand to my left hand, the uniform electric field is pointing in this direction. And my imaginary surface, planar surface, is this one right here. That's what this red planar surface is all about, okay? Can you picture that? I'm going to illustrate this planar surface now seen inside sideways, okay? So here you go. Here's my planar surface right now. Okay, so this planar surface is just coming out of the plane of my computer. And you can see that this planar surface is making an angle of 90 degrees with the electric field. I'm also defining my area vector pointing from the right to the left. And it is going to be perpendicular to the surface, right? Perpendicular to my imaginary surface. So the electric flux going through this specific surface is going to be given by the electric field that's uniform times the area of this imaginary surface times the cosine between the electric field and the area vector. Since the electric field and the area vector are parallel to each other, we're saying that this angle between them is going to be 0 degrees, and that's what's going to be the electric flux, E times A, right? Or where big A is one side of the plane multiplied by the other side of the plane, right? What lowercase a and lowercase b is all about is exactly what you see right in here. You know, the width of my plane, and let's say the length of my plane B. That's how we determine the flux. But that's a very simple flux here. That's the case of a flux of the flux of a uniform electric field. If the electric field is not uniform, it may be a little bit more difficult to calculate the flux, okay? But let's keep on looking at that. Okay, let me write down in my notes. Okay, for uniform electric field, the electric flux is given by the following equation, okay? Given a uniform electric field of strength, right? E, comma, find the electric flux going through an imaginary plane of length. The length is going to be B or A, let's see. Of length B, okay, and with of length B and with A, where this plane makes an angle, where the surface of this plane, makes a 90-degree angle with the electric field. I'm going to put that as an example, right? Example. Imaginary plane, not imaginary place, right? Okay. Solution. Okay. Here you go. Very simple example. Electric flux is E times the area of the imaginary plane the area of the imaginary plane is AB, and the angle between the electric field and the area vector is always normal or perpendicular to the plane, is going to be 0 degrees. 0 degrees, right? Let's see if I can do that. Yeah, I got it. That's the definition of electric flux. Cosine of 0 degrees is equal to 1. So that's what's going to be the electric flux. Now we can repeat this to another example, okay? Given a uniform electric field, another situation, another different plane. Given a uniform electric field of strength A, find the electric flux through an imaginary plane of length B and width A, where the surface of the plane makes a 0 degree angle with the electric field. Okay? Now it's a different problem. I'm going to illustrate that for you. Okay. It's not this case because the plane makes a 90 degree angle. That would be the case, okay? The plane is parallel to the electric field. Now the area vector is perpendicular to the electric field, the area vector of this plane. So now the electric flux going through the surface is basically grazing the surface, and the electric flux is going to be 0, right? So here you go. Now the area vector makes a 90 degree angle with respect to the electric field, and this electric flux is going to be 0. And then we can come up with another example that's in between the first and the second example. This plane now is making an angle like that. Okay? Let's say making an angle phi. The plane makes an angle phi. Not the plane, but the area vector makes an angle phi with the electric field, right? So another example here. Example, given a uniform electric field strength A, find the electric flux through an imaginary surface of length B and width A, where the surface of this plane makes a where not the surface of this plane, where the area vector, of this plane, right, makes an angle phi with the electric field. Symbol. Here you go. Just like before, we will have to replace right, the phi with in the parentheses of the cosine. And then we finally, okay, we don't even need the last one. We finally have this electric flux that's going to be a fraction of this maximum flux. That's one example of electric flux. 4 more minutes to go, right? Let's see what I can keep on covering here. Let's try another different example, not a uniform electric field, right? But let's see, here you go. Let's try this example right in here. You have a point charge. You know that the electric field radiates away from the point charge. And this electric field has a spherical symmetry. Do you see that? The magnitude of the electric field here at this point is the same as the magnitude of the electric field at this point. Okay? And you picture that? The field is not uniform. The field is not uniform because it has different directions. But the magnitude of the field on this spherical surface is the same throughout the surface. Okay? Let's see if I can get, here you go. Here's the electric field, right? One electric field vector. Electric field 1, electric field 2. They all have the same magnitude, but they're not the same because they have different directions. In addition to that, we have the vector area A that is normal to this surface, okay? That's what I illustrated right in here. This vector A is normal to this surface. Now I want you to calculate the flux. And the electric flux going through this surface of radius r. Okay? It's a problem that's a little bit more difficult than the other. So let's do that. What time is that? 2 more minutes to go. I think we can finish. Okay, example. Given a point charge of charge Q, right? Let a point charge Q, let a point charge Q. Let's put it this way. Let a point charge Q, charge Q, find the electric flux going through a spherical surface of radius r, centered at the charge. Okay, solution. We can calculate that. This one we can calculate. Okay, so here you go. We use the equation that we had before, the definition of electric flux. Okay, which is going to be EA cosine. Don't forget, A is the area of the surface, okay? And cosine of the angle of E and A. Okay, so here you go. The area, the electric field is going to be given by KQ over R. 1250, we're almost over here. You know, 4/3 the area of the spherical surface. 4/3 of pi r, r square, right? No, it's not 4/3. Sorry, 4/3 is the volume. 4 pi r square. That's what the area of the sphere is. The angle between the electric field and the area vector is going to be 0 degrees. Okay, and now we're going to finish. We finished this problem. 1 minute late. Here you go. Cosine of 0 degrees is 1. We can cancel out this r with the other r, and that's what we get for the flux going through, electric flux going through the surface of this sphere. Okay, so let's stop here. And do you have any questions? I have office hours right now. If you want to hang around, I'll be here for the next hour.
Thank you.
Thank you.
Yes, I have a question.
Yeah.
You said that you were gonna the lab
Yeah.
you're gonna upload it on Wednesday, or when are you
Yeah.
gonna upload?
Yeah, the
Oh.
spreadsheet for the lab, I will upload it on Wednesday.
Oh,
Okay.
and when is it due?
It's going to be due the next lab. Let's see how it goes on Wednesday. You know, sometimes I give you a little bit more of time because it's the first lab. Okay, so but in general, each lab is due the next lab meeting. Okay,
Okay.
that's That's how I do it in general. It's not all the time, but in general, it's like that.
Okay, thank you.
How do I lower my hand here? Let's see. Let me stop sharing. Oh yeah, here you go. Good.